This is ChainMind, the decentralized AI network built for everyone. Just search ChainMind on Google, sign up, download the app, and you're in. That's it. You've joined the network. Run it on any device, phone, laptop, or server. Why ChainMind? Fully decentralized, fully yours.
The next breakthrough in artificial intelligence might not come from a new algorithm or a faster GPU, but from a reactor the size of a warehouse that can power an entire AI campus without a single carbon atom in its tailpipe. Imagine a power plant that can be shipped in containers, assembled in weeks, and then deliver clean electricity at a price so stable that the cost of training the biggest language model becomes a predictable line item rather than a gamble. AI workloads have become the new industrial revolution, and the electricity they consume is the new raw material. When you train a state-of-the-art language model, you're not just using a few megawatts, you're tapping into the equivalent of a small city's annual power demand. That demand scales faster than any traditional data center expansion plan, and it forces cloud providers to rethink where they locate their GPU farms, how they price their services, and even how they design their models. The three criteria that keep executives up at night are simple on paper: zero carbon emissions, a capacity factor that never dips below 95%, and the ability to crank out megawatts on demand. Renewable farms can deliver green power, but wind and solar are at the mercy of weather, and battery buffering adds cost and complexity. Natural gas peaker plants can fill the gaps, but they betray ESG promises and expose operators to volatile fuel markets. The industry is stuck between a rock of reliability and a hard place of sustainability, and that tension is where TerraPower's fast reactor steps onto the stage. At the heart of TerraPower's offering is a sodium-cooled fast reactor, a design that flips the conventional nuclear playbook on its head. Instead of using water as a coolant and relying on a thermal neutron spectrum, the reactor runs a fast neutron chain reaction in a compact core, surrounded by liquid sodium. That sodium can reach temperatures above 500 degrees Celsius without the high pressures that make steam cycles risky. The result is a power plant that can squeeze more energy out of each kilogram of fuel, shrink its physical footprint, and move heat around faster than a traditional light water reactor. What makes it truly revolutionary for AI operators is the way the plant's waste heat is harvested. Instead of feeding steam into a Rankine turbine, a process that caps efficiency at around 33%, TerraPower couples the hot sodium loop directly to a high-efficiency Brayton cycle. In a Brayton engine, the hot gas expands through a turbine and then is cooled, a process that can push conversion efficiencies up to 45% or more. That extra 10% isn't just a number on a spec sheet, it translates into dozens of megawatts of usable electricity for every reactor module, shaving both the capital cost of the plant and the operating expense of the data center that draws its power. But here's the part most people get wrong: the advantage isn't just about raw efficiency. The Brayton loop also produces electricity that is incredibly stable, low latency, and free of the flicker that can plague renewable heavy grids. AI clusters are sensitive to voltage sags and frequency deviations because a single hiccup can cause GPU throttling, training runs to abort, or inference latency spikes that break service-level agreements. By delivering a clean, continuous power profile, TerraPower's integrated system eliminates the need for separate battery banks or backup diesel generators. The result is a dramatically lower total cost of ownership for the data center tenant. Capital expenditures shrink because you no longer have to overbuild renewable capacity or buy expensive storage, and operational expenditures fall as fuel costs remain fixed and the plant enjoys a near-perfect capacity factor. In practice, a 500 megawatt fast reactor can be up and running within 24 months, a timeline that matches the aggressive rollout schedules of hyperscale AI campuses, which often need new compute capacity every 12 to 18 months to stay competitive. When cloud giants and enterprise AI teams issue requests for proposals for new campuses, they evaluate a handful of hard numbers: carbon intensity, measured in grams of carbon dioxide per kilowatt hour, price per megawatt hour, reliability measured by availability above 99.9%, and proximity to fiber backbones that determine latency. TerraPower checks every box. The fuel cycle of a fast reactor is essentially carbon neutral, satisfying the most stringent ESG mandates that are now baked into procurement contracts. Fixed fuel costs and a high capacity factor lock in electricity prices, insulating data center operators from market swings in natural gas or coal prices. The reactor's safety architecture, passive shutdown capabilities, low-pressure sodium loops, and a negative temperature coefficient that automatically throttles the reaction if temperatures climb, drastically reduces forced outages, pushing reliability well beyond the 99.9 threshold. And because the plant is built from factory-fabricated modules, it can be sited next to existing fiber corridors or even co-located with other critical infrastructure, shaving milliseconds off network latency, a competitive edge that matters in AI inference where every microsecond counts. Regulators have traditionally viewed fast reactors with a mix of caution and curiosity, given their departure from the well-trodden path of light water technology. TerraPower, however, has taken a proactive stance, working hand in hand with the U.S. Nuclear Regulatory Commission to streamline licensing and embed safety by design principles from the outset. The low-pressure sodium coolant eliminates the risk of high-pressure steam explosions, while the sealed primary system reduces the chance of coolant leakage. A negative temperature coefficient means that as the reactor gets hotter, the nuclear reaction naturally slows, providing an inherent safety buffer without the need for active control systems. These features not only satisfy regulators but also address the public's lingering fear of nuclear accidents. By demonstrating that a fast reactor can be as safe, if not safer, than the conventional plants that already dot the landscape, TerraPower is paving the way for broader acceptance and smoother permitting processes, critical factors when you need to break ground on a new AI hub within a year. The implications for decentralized AI networks like ChainMind are profound. ChainMind's architecture relies on a mesh of low-latency inference nodes scattered across the globe, each node needing reliable, carbon-free power to stay online and competitive. Traditional renewable solutions force those nodes to depend on distant grid connections, exposing them to variability and requiring costly on-site storage. A modular fast reactor can act as an anchor for a regional microgrid, delivering stable, high-quality electricity directly to a cluster of edge compute nodes. Because the reactor's footprint is compact, it can be co-located with data center facilities in secondary markets, bringing power generation closer to the network edge and reducing both transmission losses and latency. Moreover, the plant's ability to provide ancillary services, such as frequency regulation and grid inertia, means that the same infrastructure can sell those services back to the broader grid, creating a revenue stream that can subsidize the cost of the compute nodes themselves. In this way, TerraPower doesn't just solve a power problem, it creates an ecosystem where power generation, grid services, and AI inference are tightly interwoven, allowing ChainMind to scale without sacrificing sustainability or performance. No technology is without challenges, and the fast reactor path is no exception. Public perception of nuclear energy remains a hurdle, especially in regions where anti-nuclear sentiment runs deep. Securing financing for a plant that sits between the proven but aging light water fleet and experimental designs requires investors to be comfortable with a nuanced risk profile. The supply chain for ultra-pure sodium and specialized alloy components is still nascent, and any bottleneck could delay construction schedules. Finally, operating a sodium-cooled reactor demands a workforce with very specific expertise, a talent pool that is currently limited to a handful of countries. TerraPower's success will hinge on transparent stakeholder engagement, strategic partnerships with local utilities, and robust training programs to build a pipeline of qualified operators. If those pieces fall into place, the technology could become the backbone of AI-grade power generation for the next decade and beyond. Looking ahead, the convergence of exploding AI demand and the urgency of decarbonization sets the stage for a new class of AI-grade power plants. Fast reactors equipped with high-temperature Brayton cycles could become the standard for any data center campus that needs megawatts of clean, reliable electricity on a tight schedule. As AI clusters sprout in the Pacific Northwest, the Gulf Coast, and even across Europe's emerging AI corridors, the modular nature of TerraPower's design allows the same plant to be shipped, assembled, and commissioned in vastly different regulatory environments with only minor adaptations. In the longer term, the same high-temperature output that feeds a turbine could be redirected to provide direct process heat for next-generation AI hardware cooling systems, creating a closed-loop energy ecosystem where waste heat is turned into a useful resource rather than a loss. That kind of integration would push the carbon footprint of AI workloads down to levels we can't even imagine today. In short, TerraPower's hidden edge isn't just a clever engineering trick, it's a strategic lever that aligns the economics of AI expansion with the planet's climate goals. By delivering high-efficiency, low-carbon power in a package that can be deployed quickly, sit close to network backbones, and provide grid services that generate extra revenue, the fast reactor could become the decisive factor in who wins the next wave of AI infrastructure contracts. For cloud providers, investors, regulators, and decentralized compute networks like ChainMind, the message is clear: the future of AI power is nuclear, and it's arriving faster than most people think. If you want to stay ahead of the curve, keep an eye on how TerraPower's reactors are being integrated into AI data center strategies, and watch how decentralized networks like ChainMind are leveraging this new power source to build resilient, low-latency inference layers around the world. Follow ChainMind for the latest updates on how cutting-edge energy solutions are reshaping the AI landscape, and join the conversation about building a sustainable, high-performance future for artificial intelligence.